Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Let's now talk about counting conjugates. Since conjugation is such an important operation in the study of groups, it would be nice to have some handle on the number of conjugates of a given element. Or put it a different way, the size of the conjugacy class of an element. And to this end, if we have three elements, A, X, and Y, and G, then A to the X is equal to A to the Y, if and only if A to the Y inverse X. Now these are not exponents, they're conjugates. Right? So we're conjugate A by X is the same as the conjugate of A by Y, if and only if the conjugate of A by Y inverse X is equal to A. This follows from the properties of conjugates. If you conjugate both sides by Y inverse here, you'll get this. And this holds if and only if Y inverse X commutes with A. Well, this prompts us to consider the set of elements in the group G that commute with a given element A. We've talked about the center of the group. Those are the elements that commute with all elements of the group. Now we're looking for the elements that commute with a single given element A. Here's a definition. The centralizer, which I will denote this way, of an element A in G is the set of all elements of G that commute with A. And here it is in symbols. We can also define the centralizer of a subgroup of G as simply the set of all elements that commute with every element in the subgroup. So it is in fact the intersection of the centralizers of every element in the subgroup. And it's not hard to see that these are subgroups. The centralizers are subgroups. I'll leave that for you. But now this earlier set of biconditionals can be written this way. The conjugate of A by X equals the conjugate of A by Y if and only if Y inverse X lies in the centralizer of A. That's just another way to say that Y inverse X commutes with A. But this holds if and only if this coset is equal to this coset. So an element A has one distinct conjugate for each coset of its centralizer. So A has precisely this many. This is the index of the centralizer in G. It has this many distinct conjugates. That's not bad. We have a formula anyway. Of course, you have to determine the centralizer, or at least its size, when G is a finite group. This index is the size of G divided by the size of the centralizer. So here is the theorem. G is a group, A is an element of G, then the number of conjugates of A, or in other words, the size of the conjugacy class of A, is the index of the centralizer in G. And in particular, at least when G is finite, then this number divides the order of G. Let's take a look at an example, or let's say, I should say, an application of this result. We can use this theorem to show that the only permutations in Sn that commute with an n cycle, sigma, are the powers of sigma itself. So the centralizer of sigma. I dropped the Sn subscript here because we're talking about the group Sn. The centralizer of sigma is the set of all powers of sigma. And since the order of sigma is its length, we only need to go from 0 to 1 less than the length. We had an earlier theorem back in chapter 3 that told us that the conjugates of sigma are precisely the n cycles because they have to have the same cycle structure. Two permutations are conjugate if and only if they have the same cycle structure. So sigma, its cycle structure is one cycle of length n, period. And so the conjugates of sigma are n cycles. And all n cycles are conjugate to sigma. There are n minus 1 factorial n cycles. So this previous theorem tells us that the index of the centralizer of our n cycle in Sn is n minus 1 factorial. But this, because Sn has size n factorial, is this quotient. So the size of the centralizer is precisely n. So it is, since the n cycles, since the powers of sigma do commute with sigma, they are in the centralizer, but the centralizer has size n, and so it consists precisely of the n cycles. Okay. The permutations in Sn that commute with an n cycle are precisely the n powers of sigma itself. This may seem like an unimportant result, but actually we will have a rather important use for this later in the book. Okay. But it also provides a good illustration of the use of theorem 840 here, this theorem at the top. To extend this result about what permutations commute with an n cycle to a more general setting, which is something we always try to do when we can, it's helpful, as it often is, to first look at an example. So let's consider this permutation. It's not an n cycle. It lies in S7. And suppose that lambda should commute with sigma. What can we learn about lambda? Well, another way to say that is that the conjugate of sigma by lambda is sigma itself. Now we know how to take the conjugate of a permutation. First of all, the conjugate of this product is the product of the conjugates, because conjugation behaves so nicely, it's a homomorphism. And to conjugate a cycle by lambda, we apply lambda to each element of the cycle. So that looks like this. This is sigma to the lambda, and we're supposing that that's equal to sigma, which is this. Now we like to match up cycles here. And we can do that for one reason, and one reason only. Conjugation does not change the cycle length. This is still a 3 cycle, this is still a 4 cycle. And therefore, this 3 cycle has to be this 3 cycle, because it's the only one, and this 4 cycle has to be this 4 cycle. So conjugating the 3 cycle by lambda, which looks like this, actually has to be this. In other words, lambda doesn't change the 3 cycle. Conjugation by lambda. and similarly over here for the 4 cycle. So lambda acts independently on the 2 underlying sets of these 2 cycles. The restrictions then of lambda to these 2 underlying sets are permutations of those sets. And so we can write lambda restricted to mu here, sends this to this. In other words, lambda restricted to u commutes with this 3 cycle, and therefore, by what we learned earlier, must be a power of that 3 cycle. And similarly for the 4 cycle. So lambda, which is lambda restricted to u times lambda restricted to v, is a power of the 3 cycle times the power of the 4 cycle. So now we can apply the earlier result and say that the number of permutations, lambda, that commute with sigma is the product of the lengths of the 2 cycles that make up sigma. Now this argument, if you study it and it makes sense to you, it'd be relatively clear how to generalize it. The argument relied on the fact that sigma is a product of disjoint cycles of distinct lengths. It wouldn't work if the lengths of the cycles were not distinct. It would be a more complicated analysis, which we won't go into. So, if sigma is a product of m disjoint cycles, this is the cycle decomposition of sigma, of distinct lengths, then the centralizer of sigma is the set of all products of powers of,
John Creekmore,
of lambda 1 through lambda n, and the exponents lie between 0 and the length of lambda I, strictly less than the length of lambda I. So the number of conjugates of sigma is this the size of the conjugacy class. It's this index, which now is n factorial divided by the product of the lengths. We can mimic this result, or the earlier results, the stuff we've been talking about. In particular, let me go back here and find it. We started with this set of biconditionals after we defined the centralizer. And this was the starting point for our analysis. So we can redo this, not for elements A, but for subgroups H. So we first need the definition that corresponds to the centralizer of an element, and it is the normalizer of a subgroup. Okay? Those are the elements that normalize H. In other words, they fix H under conjugation. The size of the normalizer, the size of the conjugacy class of H, the number of conjugates of H by G, is the index of the normalizer. And the proof is the analog, direct analog of what we did earlier. So I will leave it for you to discover the proof. I'm going to hide it, so it's a good it's a good practice for you. Let's talk about an application of this result, actually both of the conjugacy results for elements. It's a critically important application that demonstrates the power of this analysis that we have been doing. Okay. These formulas, both for the size of the conjugacy class of a single element and the conjugacy class of a subgroup, are very useful in the study of finite groups. And here is a really important example of that. Suppose G is a group of order p to the n, where p is prime. Groups of this type are known as p groups, and we will have quite a bit more to say about them later in the book. But for now, let's observe that if A is an element of G, then the conjugacy class has size equal to the index of the centralizer, and we've already observed that this divides the order of the group. Any index will divide the order of the group, which is p to the n. So the size of each conjugacy class is either 1, if it's trivial, or a positive power of p. When is the conjugacy class trivial? Have size 1? Well, the element A commutes with itself. And so this would say that there are no other conjugates of A, and so every element of the group, when you conjugate it, use it to conjugate A, gives you A again. In other words, A is in the center. A commutes with all elements of the group, so all the conjugates collapse. Okay. Well, the conjugacy classes, they are equivalence classes for the relation of conjugacy, so they partition the group, which means that we can compute the order of the group, which is p to the n, as the sum of all the conjugacy classes. And I've separated out the conjugacy classes of size 1. There's one of those for each element in the center. So when I take the sizes, I get the size of the conjugacy classes, including the size of the center. So otherwise, if I didn't do that, I'd have a bunch of 1s, and the number of terms would be equal to the size of the center, so I just collected them all. These sizes, then, because these conjugacy classes are not trivial, they're divisible by p. But p to the n is divisible by p. Therefore, the center, the size of the center, is divisible by p. So the center, we have just proved that the center of a p group has size at least p. It's divisible by p. So we can say a little more, but the main point is it's at least p, and therefore contains some non-identity elements. In fact, p minus 1, at least p minus 1, non-identity elements commute with everything. They're in the center. This is tremendously powerful stuff. This theory has shown us that a p group will have non-trivial elements in the center, non-identity elements that commute with everything, and in fact at least p minus 1 of them. And who would have guessed when you first learned about groups that if a group had prime power order, then it would have to contain some elements that commute with every other element, with all elements. This is pretty impressive analysis. In particular, it tells us something about groups of order p squared. Since the center is divisible by p, it has size either p or p squared. But actually it can't have size p, because if it did, the quotient group would have order p and would therefore be cyclic. And I'm going to leave it to you to show that if that happens, the group must be abelian. And that's a contradiction to the size of the center is p, because abelian groups, their center is the whole group. So the size of the center must be p squared. In other words, G must be abelian. So in summary, any group of order p squared, or p is a prime, is abelian. Okay? That's another remarkable demonstration of the power of this theory. And here is a theorem that summarizes what we've just discussed.